It's time for fun with math, and today we're going to talk about graphing, or in general, trigonometric functions. But we're going to start with this little activity, which we'll also do in class, on how do you graph trigonometric functions? What do they actually look like? It's not too hard to do if you think about how the values work on the unit circle. The idea is you have these inputs, which we call angles here. So here's 0 degrees, here's 30 degrees, or if you want pi over 6 radians, pi over 4 radians, pi over 3 radians, and then pi over 2 radians. So these are sort of like our input values. Here's pi radians over here, 3 pi over 2 here. And of course, then 0 winds up being 2 pi radians. And we can keep going around and around and around. And those are our input values. So here we'll put 0, and then we'll put pi over 2. And then we'll put 3 pi over 2, or pi. And then we'll put 3 pi over 2. And we'll need to extend this line a little bit further. And then over here, we'll put 4 pi over 2, or 2 pi. And so the angles are our inputs, and then the outputs are given on the unit circle. So because we're doing sine of x, these are actually the outputs of the unit circle. So if you look at 0 radians, you'll see the output is 0. So sine of 0 starts here at 0, 0. And then at pi over 2, the sine is 1. And so at pi over 2, we're at height 1. So we'll put a little point here. And we can keep going around the unit circle, seeing what the sine is. So here, at sine of pi is actually, back to 0. It's the output here. And so at pi, you're at 0 again. And we can keep on going. At 3 pi over 2, now the output is negative 1. So we're down here at negative 1. So put negative 1 here. And then you get back to 2 pi, and so we're at the output of 0 again. So we're at 0. And then we can simply connect the dots. And so when we connect the dots, it just basically comes up and sort of levels off, and then comes down and levels off again right here, hits that point, comes down and levels off right here, then comes up, and we'll stop it right there. And so what we have now is that this is actually a graph of the sine function, and it continues on in both directions, right? So it'll continue to go up, and then it'll turn around and come down again over here. And I guess if you want, you could tell me what it is right here. So it'll continue going up until you get yet another pi over 2. So this is going to be 5 pi over 2. And it'll keep on going, and it'll just keep on repeating, and then it'll turn around, and then it'll go down again. And then over here, it'll keep on repeating. It'll go down. It'll hit a bottom, and then it'll go back up. And so this will be negative pi over 2. And so on. It's what's called a periodic function, because a function just repeats after a certain period. So if you look at this, we can talk about the domain, the range, and the period, and finally the symmetry. Basically, is it even or is it an odd function? We talked about these near the beginning of the semester. So let's just talk about the domain real fast. So the domain, remember, are all the input values. So if you look along the x-axis, these are just the degrees or the radians, right, the angle. And so everything is in your domain here. You'll see a graph above or below it. So my domain is everything, minus infinity to infinity. Whereas the range is limited a little bit. So you'll notice in the range here that you don't fall below negative 1 and you don't go above positive 1. And that's because the outputs on the unit circle are between negative 1 and positive 1. And you want to include the endpoints because you do hit negative 1 and you do hit positive 1. So there's the range. The period, it's sort of the distance here on the x-axis it takes for it to repeat. So notice, you just pick any old spot, starts here, and sort of goes up, and then it levels off, and it comes down, and then it comes down here, and then it goes up, and then it repeats after that. So my period is from 0 to 2 pi, so we'd say our period is 2 pi. It's basically the smallest distance until it repeats on the x-axis. And then is a function even or odd? So remember the idea of this. An even function, the idea is that the outputs on either side of the y-axis are exactly the same. So, here's an output here, and here's an output down here. They're certainly not the same, they're the opposite of each other, so it's not even. But remember what an odd function looks like. Instead of having the same value on either side of the x-axis, so instead of this being true, they have opposite value. This is true. So negative f of negative x. And that's what this is saying. So up here it's positive 1, and on the left-hand side it's negative 1. So this is an odd function. Now we'll talk about the other functions, how we understand these as functions like cosine of x. And we'll talk also about tan of x. And then we'll see the reciprocals. Right, so we'll see the reciprocal of sine of x, which is cosecant x, the reciprocal cosine of x, which is secant x, and the reciprocal of tan x, which is cotan of x, how to graph those using these same ideas and an activity we'll do in class. But that's how you graph basically a trigonometric function using the unit circle. So that's what we're going to do today. So what are trigonometric functions? They're basically functions with periodic rate of change. Let's take a look at a bunch of them, and we can then talk about sort of their domain, range, period, symmetry, and even versus odd functions. So here are all the trigonometric functions, and maybe a little hard to see on the screen, but you can look at your paper. So here's the sine of x, which we just did, and it tells you the domain here is all real numbers. The range is -1 to 1, including the endpoints, and the period is 2 pi. The cosine of function, notice, looks very much like the sine function. It's just sort of shifted back by pi over 2. All right, so cosine and sine function are very similar. And if you think about the unit circle, that's true. The inputs and outputs in the unit circle are very similar to each other. And the tan of x looks a little funny. It actually has these vertical asymptotes here. Right? Now, you may ask yourself why it has vertical asymptotes. And remember, the sine of x, how the tan of x is actually can be rewritten as sine of x over cosine of x. So you'll notice it has vertical asymptotes when this denominator here, cosine of x, when that's equal to 0. And so at pi over 2, you have a vertical asymptote because at pi over 2 here, cosine of x is 0, and so on. So that has vertical asymptotes. And then the cosecant of x, the secant of x, they look a little funny, but you can kind of see they're going to have vertical asymptotes because the cosecant of x is 1 over sine of x. So whenever the sine of x is 0, little vertical asymptote. And similarly over here with 1 over cosine of x for the secant of x. And here's cotan of x. It looks very similar to tan of x. It's just the reciprocal, so it also has vertical asymptotes. And we'll talk about that when we do the activity in class. But you should be kind of familiar with these top three. So you really want to know the graph of sine of x and cosine of x and tan of x. And I'll show you in class how you can use these three to actually find these three here. At the same time, though, you could just use your calculator. So let's talk about how we can use a calculator to graph the secant of x. So if you have a calculator, let's take it out. And we want to graph this thing. So to graph the secant of x, what we can do is just turn on your calculator. We'll hit mode and make sure you're in radians. You should be in radians. And then we'll hit y equals. And then remember, the secant of x, is really, it's really 1 over cosine of x. So to graph secant of x, what we're going to do is we're just going to graph 1 divided by cosine of x. And then we'll make our window. It really doesn't matter how you make your window, but maybe, since the periods of these seem to be about 2 pi, maybe we'll go back. Let's do minus 4 pi. So minus 4 pi, and then enter, and we'll put 4 pi here. And we'll put enter. And then let's just hit graph and see what happens, see what it looks like. So that's what it looks like. You just get these sort of upside down looking parabolas, and so you can kind of just trace this graph onto your paper here. So if you look, it has some vertical asymptotes right here and here. So let's just put some vertical asymptotes on here, and then we'll try to figure out where they're actually at. So here are my vertical asymptotes, right here. Here's another vertical asymptote, and we're just going to repeat these. They're basically the same distance apart, which we don't know that distance, but we'll figure it out here in a minute, and that should be enough. We'll do one more over here. So just put a vertical asymptote here, put a vertical asymptote here, and these are supposed to be the same distance sort of apart the best you can, and we'll put one here. And then what you want to notice on your calculator is it comes all the way down, but doesn't quite hit the x-axis. So it's probably hitting the number 1 down here if you think about it, because it's 1 over cosine of x. And the cosine is not going to be bigger than 1 or smaller than negative 1. And that's because it's on the unit circle. So the next thing you might want to do is we might want to just, we'll just label this height 1 and this height negative 1. And we can just draw some dotted lines. These are not horizontal asymptotes, but they're just a sort of guide to help us along here when we draw the secant of x. So I'm just going to draw this here. So I don't want to go above that line, and I don't want to go below this line. So when I draw it, you can just see what it looks like. It looks kind of like a parabola, so I'm just going to draw it on here. So I'm going to take my pen, we'll do it in red, let's say, and so it's just going to do something like this. So it goes down like this, and if you look at your graph, the next one is going to go, instead of up here, it's going to happen down here at the bottom. So we'll draw that one, and it just repeats going from top to bottom. So right here, just kind of draw it like this. And I guess we should hit that. We've got to hit that line. So like this, and then up here, like this. And then over here, down here now, like this. So these are just some guidelines. All right, and it's going to hit this height at some point. So if you want, you can put little circles here, because I know it's going to hit that point. And it comes down like this and goes up. I'm just basically trying to draw it, graph it the best I can from my graphing calculator. And that's what the secant of x looks like. Now, we should probably label the sort of inputs here that give you vertical asymptotes, and that's going to happen. That's going to happen when this cosine of x is equal to 0. So if you think about when that occurs, right, when cosine of 0 is 1, and then cosine of pi over 2 is 0. So I bet that's pi over 2, and that's the same distance, but on the other side, so negative pi over 2. So I'm going to use some symmetries here. And so then that's pi over 2. If you add pi over 2 again, you get here, which is pi. Add pi over 2 again, I bet that's 3 pi over 2. Add pi over 2 again, that's 4 pi over 2. Add pi over 2 again, and that's 5 pi over 2. So you can label each of these spots, right? This was pi. This would be 2 pi. Right? And then you can go the other way too. So negative pi over 2. You subtract again pi over 2, it's negative pi. Then negative 3 pi over 2. So you can just use the symmetry here. And then this is going to be negative 2 pi, where it's actually positive 1. And then right here where it has a vertical asymptote, it's negative 5 pi over 2. We can now use this graph to actually find the domain, and the range, the period, and the symmetry of it. So let's talk about the domain first. Remember, the domain is just these input values. So if you look along here, you have some vertical asymptotes. So basically, my domain for this function would be everything, but you want to throw out these points. Right here, we have these vertical asymptotes. So I'm going to put little open circles here because I'm going to throw out those points. And it's all this stuff. So to write it down, it's a little kind of confusing at first, but then it makes sense if you think about it. So the first place I'm going to start is between here, negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2, that's in my domain because I have a graph above or below the points in between here. And then I'll use parentheses, then union, then from pi over 2 to 3 pi over 2. That's in my domain. So from pi over 2 to 3 pi over 2. And then I'm just going to write union dot dot dot. So continue sort of in that pattern. And then I'm going to go back the other way too. I'll do one of these. So from basically negative 3 pi over 2 to negative pi over 2. So here I have negative 3 pi over 2 to negative pi over 2. And then I'm just going to write union dot dot dot, right, in that way. Right, so that's my domain there, and then the range is a lot easier to write down. So if you look at the range are the output values, and so for the output values, you're good until you get up to here, and so you stop here, but you want to include negative 1 because there's a graph to the right or left of negative 1. Now there's no graph between here to the left of the right, but then you pick up at 1, and you're good all the way up. And so for my range here, I'm going to do negative, parenthesis here. So parenthesis, negative infinity to negative 1, square bracket, because you want to include negative 1, union, square bracket, you get to 1, you want to include it, and then all the way to infinity. And so that's all the things that the graph hits for the output. And then for the period, so for the period you want to see when it repeats. So it doesn't matter where you start. Let's just start here at 0. So you can see it goes up here, and it goes all the way up, and then down here, and it goes all the way down, and then up here. And then you're going to stop here because after here you'll notice it repeats again. So you basically draw this graph. So the period is from 0 to 2 pi. And so the period is just 2 pi. It's that smallest distance until it repeats. And of course the symmetry, so remember we have two types of symmetry we're talking about here. It's either even or it's odd. And if you think about this, remember the idea of even is sort of like this, and the idea of odd is sort of like that. So that's kind of what comes to my mind. Sort of if you say an even number, I think 2, and you say an odd number, I think either 1 or 3. And so if you look here, you take a point over here, so some input value, you get out a point. Go to the opposite side, you actually get out the same output value. So since these have the same height, not opposite height, we say this is even. Right, so remember the actual definition for even is the function is the same on either side. So f of x is equal to f of negative x. And then for odd, it's not the same, it's the opposite. So f of x is equal to negative f of negative x. And so that's how we figure out the domain, range, period, and symmetry from the graph. So that's how you can graph a trigonometric function with your calculator, kind of a complicated one. And you can do them easier ones too, you know. So if you want to graph like what we did, the sine of x, you just come in here and clear this out and graph sine of x. And if you hit the graph button, you'll get a graph of sine of x, which just goes up and down, up and down. If you want to get a better window here, you know it actually goes between -1 and 1. So you could zoom fit it, or you can just hit -1 to 1. And it gives you a nice graph of sine of x. So there's a graph of sine of x. All right, so let's move on here. So we talked a little bit about the other trigonometric functions, which we'll do a little more in class. You know, the domain versus the range. There's sort of periods, there's symmetries, even or odd. We'll do an activity in class about that. But I want to talk about sort of trigonometric models. So here, this is the sort of standard formula for a trigonometric model. It's used to model things like sound waves or wave phenomenon in general. And so we have something called the amplitude, which is your A. Right, so A is called the amplitude. It's actually the absolute value of A. And then we have something called the period. Right, so this trigonometric model will have a period, and the period is actually given to you by 2 pi divided by b. So you just take this b and take 2 pi divided by it. And there's something called this phase shift with this c over b. So it's kind of a shift of your wave. And then, of course, plus d here, there's not a word for that, but if as terms of transformations, this is a shift up. And we kind of want to understand each of these things and how they're connected with transformation. So let's take a look at the sort of example I prepared for you guys. So here we're starting with a sine wave, just sine of x, and we want to understand basically, you know, this sort of g of x, which is equal to let's rewrite this, sine of b x minus c plus d. So the way that I understand this is I actually factor a b out of the top. So down here you'll see there's this period 2 pi over b, there's this phase shift c over b, and amplitude absolute value of a. If you want to understand the phase shift, really you just got to re-look at this formula and think of it like this. You have a and then sine of, and you can actually pull a b out of this expression. So it's going to be times something minus something, and then this is all going to be plus d. And of course the somethings, it's like something goes here times b is x, and so that's just the x. And then something here times b is going to be your c, and of course that's the c over b, which you'll see that's actually the phase shift. And so if you think about this in terms of transformations, you can see what it does to a normal sine wave. And to see this, you don't actually need the entire sine wave, so I'm going to delete some of this. You only need a single piece of the sine wave. Everything else just repeats. So we're going to take this piece of our sine wave, and we're going to think about this in terms of transformations. So remember transformations, you're going to work out with the inside first. So in the inside, we're right here. And we're going to do opposite the order, remember? So instead of taking away the c over b first, we're actually going to work with the times b first. And if you multiply something by b, you want to think horizontally. I want to think it's actually a stretch, but it's the opposite of what I think. So it's actually a shrink by a factor of b. So if you see this, we're going to take this thing and we're just going to shrink it by a factor of b. So it's like 2 pi is going to compress it horizontally by this little b here, and it's going to shift us down, basically compress us right here. Right, everything's the same, it just becomes a little smaller. And that's what the period now is, 2 pi over b. So it just compresses it horizontally. And then we want to do this phase shift. Okay, so this idea of this phase shift is actually a shift to the right, c over b, and that's because it's a transformation. So look, this is minus c over b, right? So minus, I want to say it's going to go to the left, but it's actually to the right, c over b. So we're going to take this thing, we're just going to shift it over right here. All right, so we did the transformation, the sort of we shrunk it by a factor of b over here. We shifted it to the right by c over b, and now we get to the outside stuff. And now when you're working with the outside, remember, everything works just how you like it. So this a is actually a vertical stretch by a factor of a, and then this plus d is a shift up by d. So let's see if we can't get this to work. We'll have to kind of move it around a bit. But here, we want this, we just want to keep it kind of where it's at, and then force it to go up. So we have to play with it a little bit, and then we force it to kind of vertically stretch. We'll have to move it around here, but keep stretching here. All right, gotta break it here, and then there it goes. So vertically stretch it, and then we can move it up like this. And it looks like we stretched it vertically too much, so I want to stretch it back. Gotta break it again in there. So let's break it. There it goes. And so here, there we go. And so this right here is sort of just stretching it vertically by a factor of a. And then we can just take this and shift it up d units. So we just shift it up, push it up here, and there's our new trigonometric model with these factors included. So basically, it has an amplitude of a. So the height from here to here is a. The height from here to here is a. It has a new period of 2 pi over b. So you can see we sort of compressed it a bit. And it has a phase shift of c over b. It just shifted over. And then if you want the rest of the graph, all you need to do is just copy it and paste it. And then we just connect the pieces together. So there's one piece there. And then we can do it again, and we can get another piece on this side. But that's the graph of our sort of new function. Let's see if we can't put this all together. All right, so over here, let's do an example. So in this example, we want to use the amplitude, period, and phase shift to graph the function. Basically, that is to say, we're going to use transformations. So you'll be given these formulas. You don't need to memorize them if you don't want to, but here, if you have f of x equal to, and then you have this 3 times sine, that's not what I want to do. If I have my general formula, f of x, and let's move this up so I have more room. So here is our general formula, f of x is equal to a sine of bx minus c plus d. So I know my period, p, is given by 2 pi over b. My amplitude is given by absolute value of a. And then, of course, my phase shift is given by c over b. And so you don't have to memorize it in terms of transformations if you don't want to, as long as you understand what these words mean. And so here you can see, here's my a, here's my b, here's my c, and there's my d. And so I know my amplitude. If you want, my amplitude is equal to absolute value of 3, which is just equal to 3. And then my period, p, which is the same thing as 2 pi over b, and I can just plug and chug, so it's 2 pi divided by 2. So my period is really just pi. And then my phase shift, of course, the formula says it's given to you by c over b, so I can just plug and chug if you want to. And so when I look at this, it's like, oh, my c is pi over 3, and then divided by 2, which is really pi over 6. So that's my phase shift. And so given this information, I can actually graph this function f. And the way that I like to do it is I have my, let me be a little bit better about this. We have our x and y axis here. So here's my y, and then here's my x. And I can just draw sort of a normal sine function, right? So a normal sine function would start here, and it would go up and then come down, and then go down here the same way and come back up. So there's a normal little sine function right there, and it just repeats, right? So it comes up again, and then it goes down, and the same other side does exactly the same thing. So that's just a normal sine function here. So this is 0, this is pi, this is 2 pi. And so what we want to do now is we want to try to incorporate this information. So our new sine function, our new trigonometric function, new trigonometric model, should have a amplitude of 3. So what we can do is we can draw our new one. We'll have an amplitude of 3. So here's 2, and then here's 3. Let's put 3 right here. And then let's put 2. Let's put 3 right here. So we'll make this a little bigger. It's -1, -2, -3. So we'll have an amplitude of 3. And then it'll have a period of pi. So we'll fit one period within here. And it'll have a phase shift of pi over 6. So I might need to do this in sort of phases. All right, so I'm going to do in the first phase where it just gives me an amplitude of 3 and pi, so we can see what sort of happens here. So it's basically going to go up here, and then it's going to come down, and it's going to come all the way down here, and then it's going to turn around and come back up. And then of course it's going to repeat after that, but I'm going to keep it just with one period because you can just cut and paste if you need to. So there's a sine function basically with amplitude 3 and period pi. And now I need to do a phase shift. All right, so for a phase shift, I have to move it over pi over 6. So let's put pi over 6 over here. So here's pi over 6. It's basically 30 degrees. And then over here, this is going to be pi plus pi over 6, right? So pi plus pi over 6. Or if you want, that's just 7 pi over 6. And so it's going to go down, it's going to meet right here. And again, you can just kind of shift everything over a little bit. So you see here it's supposed to be 0, and then here it hits this height sort of in between. So let's just move this over a little bit right here. So that was, it's going to hit right here, and then right in the middle, we'll put a dot right here. And then we'll kind of just connect these dots so you can see it sort of just goes up. Oops, that's terrible. Let's erase that. So it's got to go up. Hit that dot. Turn around. Come down. Hit that dot. And then come all the way down again here. And turn around. Come back up. And try to hit that dot right there. Make that a little bit better. All right, so now it's a sine function, but it's out of phase by pi over 6. So it's got a period of pi, it's got an amplitude of 3, but it's out of phase by pi over 6. And what's nice about this picture is you can see what it means by a phase shift. So a phase is sort of like, this is in phase as it passes through the origin, and this is out of phase by pi over 6. All right, and then we have one last thing that we have to do, which is kind of tough. You actually have to shift this all up by 1 now. We never took, to consider that plus 1. So that's a little tricky to do. So what I like to do on here is to kind of trick the picture into the right picture. Now, of course, you can just cut and paste this blue graph and just repeat it again and again and again. And then to shift it up 1, we can be a little bit clever. What we can do is take that solid line right there, and we'll turn it into a dotted line. So we'll turn this into dotted line right here. And so instead of actually moving the graph, what we're going to do is we're going to move the axes. This is a nice little way to get this graph to work out right. And so we'll take that, and then we'll draw our new axis down here. where there was this -1, because I think we shifted it up 1, right? So we're going to shift it up 1. So we'll draw it right here. And then we'll just change our numbers. So I'm just going to delete our numbers here. And if we just delete these numbers here and we relabel them, then we'll have the right graph. Right? So we're just changing our perspective a little bit. So now remember, this is height 1. This is now height 0, then -1, -2. And then this is 2, 3, and 4. So now that blue graph, right, the blue graph is the graph of our new trigonometric function, right, using the amplitude, the period, and the phase shift. All right, so one last problem with trigonometric models, a sort of applied problem. These are kind of nice because you can use your calculator to solve them. So it says the number of hours of daylight in Boston is given by this formula. Y equals 3 sine of 2 pi over 365, x minus 79, and all plus 12, where x is the number of days after January 1st. And it says, when during the year does Boston have exactly 10.5 hours of daylight? And we'll round our answer to the nearest day. And so this is kind of a nice problem if you think about it. It's pretty easy to set up. So right here, all we need is sort of our equation. All right, it's sort of our picture in a sense. That's our formula in a sense. So they give us this. And we just got to figure out what to do with this 10.5. And 10.5 is our stuff. And so, you know, what is our stuff? Well, it's not x, because x is the number of days after January 1st. So it must be the y, the number of hours of daylight. So what we're going to do is we're going to take 10.5, and we're going to set it equal to this 3 sine of 2 pi divided by 365. Then all times this x minus 79, and all plus 12. And so there's two ways to solve this equation. We can either solve it by hand, or we can use our technology. We can use our calculator. I'm going to use the calculator because I think it's a nice use of the calculator to solve a trigonometric equation. But you can try to solve this by hand if you want to. But on your calculator, it's not too bad. It's actually pretty easy to do once you get it in right. So hit y equals and clear. And then we can just plug this in. So I'm going to plug in, I'm going to graph the right and graph the left, basically. So I have 3 sine, and then left parenthesis. Oops, I already put it on there, so not left parenthesis. So just 2 pi, so 2 second pi. And then divide by 365, left parenthesis, x minus 79, end parenthesis, and then end one more parenthesis. That closes off the sine function, and then we'll add 12 on the end. And then for y2, we're going to put 10.5. And then here's where you have to think. Once we have the right side of the equation, left side equation in here, then we have to make our window. Now, remember, this represents the number of daylight hours in a year, and x is the number of days. So for my x min, I'm going to put 0, so that starts at 0 days. And then x max, I'm going to put 365, because this was counting out the days of a year. And then I'm going to hit zoom and zoom fit, because I have no idea what the output should be. So I'm going to zoom fit it, I hit enter, and you should see basically the number of daylight hours is going to go up, and then it's going to go down. And we're looking for when it's 10.5, and you see that there's not just one time of the year, there's actually 2 times of the year that Boston will have this 10.5 hours of daylight. So I'm going to copy that picture down so I can get partial credit for my work if I make a mistake. So 0, 365, it basically went up, then it came down, draw a line here, and I'm looking for where it crosses these 2 points here, so I'm going to do intersect. And when I do intersect, it's going to tell me x is approximately, so let's see what happens. So I'm going to hit second trace, and then go down to intersect, which is number 5. Hit enter. So I hit enter, enter, and enter for a guess. It's going to take me to one of my guesses, so it took me over here. And it says 291.9 blah blah days, so about 292 days. So my first one was about 292, I guess that's my second one, 292 days after January 1st. Or there's also another one. Let's see the other one. So let's hit second trace again, go down to number 5, or hit number 5 and enter. And now first curve, second curve, that's good. But for a guess, I want to scroll over to the other one. So I'm just going to hold that down, scroll over kind of close to it. As soon as you get closer to it, then you can hit enter and it'll jump right to it. And so it's 48.5833 days, right? So what is that? About 49 days, let's say. So over here, let's say 49 days. And so after 49 days, after January 1st, so if you want 49 days, if you want, we could actually add this after January 1st. So 49 days after January 1st or 292 days after January 1st, you'll get about 10.5 hours of daylight in Boston. So that's kind of a nice application. And not too bad because they give you the formula and then you just got to solve the equation. And I usually let you guys use the calculator to solve these sort of applied problems. And then I save the easier trigonometry equation problems to do without your calculator. All right, so let's just review real fast. So what are trigonometric functions? They're basically things with periodic rate of change. And so if you think about it, that's what they're used to model. So anything like your engine, your heart rate, anything that has like a period to it, you'll use these types of functions to model it. We talked a little bit about the formulas and graphs. We'll talk more about this in class so you can understand a little bit more about the domain and range and what a period is, symmetries, or the evens or odds. And then we really focused on this sort of trigonometric model and trying to understand what these mean, like what's the amplitude, it's sort of like the height of this function. What's the period? It's the length it takes for it to repeat. And what's the phase shift? It's basically a horizontal shift to the right by c over b. And so I try to help you guys understand this in terms of transformations. And then we did an applied problem.